Welcome back. So we've talked about a fair amount of our kind of pre-calculus material at this point. We've gone about a pretty good clip, but again, hopefully, since this is recap, it's not too difficult to catch up on. So there's a few more topics I wanted to touch on before we actually dive into like the calculus part of our calculus course. So the first thing I wanted to discuss were what we call rational expressions. So in mathematical terms, that officially means an expression where you have like a polynomial when some variable over a different polynomial. I guess technically it could be the same one, but that's not very exciting. So that's what a rational expression is: polynomial over other polynomial. So generally speaking, we'll probably look at this in the context of taking some rational expressions and then putting them together. So if we were wanting to collapse them down in a sense. So let's take a look here. So I have example here. Let's see, I'll go with a minus. Yeah, so we've got 10 over x minus 2. Technically, I know it doesn't look like a polynomial, but it counts. It's, weird. So 10 over x minus 2 minus 5 over x. And we want to put those together into one bigger rational expression. So hopefully you'll remember this. You can't just add and subtract fractions like straight across. It's not 10 minus 5 over like x minus 2 minus x. Please don't do that. Hopefully you'll recall that we need to find what we call a common denominator before we can put these two beasts together. So in this instance, frequently the most straightforward way to get at one of those common denominators is to just sort of multiply your individual denominators together. That is a multiple. You might be able to do a little bit better. But so right here we have an x minus 2. We don't have an x. Let's put one in there. So we have x times x minus 2. And hopefully you'll recall one of those kind of timeless rules of algebra. If you do something to the bottom of the fraction, you've got to do the same thing to the top of the fraction, in order to keep things consistent. So we have 10x up top now over x times x minus 2. Right here, we need to multiply by x minus 2. I'll write it off, on its own because it's a little more complicated than just an x. But again, anything we do to the bottom, we also have to do to the top. So we have that. And now, once the denominators are the same, then we can just subtract the numerators from each other after we've done all the necessary algebra. So x times x minus 2, 10x up top, and I've got to distribute that 5, so I'll have 5x minus 10. Again, note the minus sign, note these parentheses. That's important because in order to make sure I do the arithmetic properly, I have to distribute the negative sign through here. So this is going to be minus 5x plus 10 hanging around in the back. So when I work out the, combining like terms there, 10x minus 5x gives me 5x minus a negative 10, like we said, is plus 10. And then down below, we have x times x minus 2. Now, we might be able to streamline this a little bit more. You'll notice 5 and 10, common factor of 5, you could pull off. If you want to do that, that's fine. But for me, this does the job. It's not, there's not really any cancellation or anything we can do to hack this down anymore. So we've got two rational expressions that we have combined together into a bigger one. And we did it, using this common denominator trick. Let's take a look at another one. Okay, up next we have 12x over x squared minus 4 plus 6 over the quantity x minus 2. So that's that's our setup here. Now technically we could do it the exact same way we did the last one, just smash these two guys together. But if you do that, as it turns out, you've kind of got some excess, some cruft, if you will, that doesn't need to be there. Because you may recall this guy over here, this x squared minus 4, he's what math types like myself will refer to as a difference of squares algebraically. So he looks like x plus 2 times x minus 2. Trust me. Boil that out, you'll get that same structure. So you can look up differences in squares if you need a reminder of it. So I'm going to go ahead and replace that right here. So, and with that in place, we don't really need to multiply like each term, top and bottom by the other denominator, because we already have an x minus 2 here. So we have an x minus 2 in both places. We don't have an x plus 2 back in the second guy. So kind of like we did with the last example, I'm going to do that. So those guys, and if you had left that as x squared minus 4, again, I don't really hold it against you. So now we have plus, I've got to distribute the 6, so we'll have 6x plus 12, and if we combine our like terms, because that just feels kind of lazy just to leave it like that, 18x plus 12 over, and again, you could technically factor a copy of 6 off this thing up top and have 3x plus 2, but in terms of putting this together, that's taking care of what we need. So just as a heads up, you could have gotten this if you had just done like a big, multiply both these things together. But the catch is you'd have like some extra terms that would turn out you could actually cancel, stuff away. So if you think about this like numerical fractions, it would mean that the thing you gave me was not in lowest terms, and that's normally what we like to see. I want to take a look at one more example of this before we shift gears a bit. All right, letter number 3. So in this instance, again, the same kind of just smash the denominators together approach via multiplication. It would work, but it's kind of overkill. So in this case, you may notice this x minus 7 and the 7 minus x, they're just opposites of each other, right? Like if I multiplied this by -1 and distributed it through, I get exactly what I have right here. So that's actually exactly what I'm going to do. Multiply the top and the bottom of this thing by -1. That's going to turn this, again, because you have to distribute the negative, with the parentheses I kind of fake drew in there, across, and that's going to change each of these signs to match that, because x minus 7 and -7 plus x really are the same thing. So we get 12 from the first guy, because we don't have to do anything to this to get our denominators in common. The only thing we've got to do is distribute that, -1 through there, so plus 3 times -1 is the same thing as -3, and I don't even need the bottom chunk of the board this time. So 9 over x minus 7. All right, so a few examples of seeing these rational expressions, kind of, taking the smaller rational expressions and putting them together into a big one. What if you need to go the other way? That's an excellent question, viewer. Every now and then we need to take like a big rational expression and break it apart into smaller ones for various reasons that you'll see over the course of the semester. I promise this really is going to come in handy. So we've got all of this stuff, this cubic polynomial, 2x cubed minus 7x squared plus 4, living over top of just the quadratic x squared. If this is more complicated than just a plain old power function, you got to dig in a bit, but for our purposes, this will do the job nicely. So what I'm going to do is kind of do the reverse of what we've been doing. I can break this up into 3 separate fractions, each with this same denominator. So we have 2x cubed over x squared minus 7x squared over x squared plus 4 over x squared. All right. Now, at this point, we can kind of cancel stuff away using our properties of exponents or whatever sort of algebraic chicanery you might want to try to pull here. So we've got an x squared over an x squared. They vanish in a puff of logic. 2x cubed divided by x squared. We've got 3 x's up here, 2 down below. We'll be left with 1 up top. What I have just done is not like standard notation, but I think you get the idea. There's not really much we can do with this 4 over x squared. I guess you could write it as 4x to the -2nd, but the rational thing is fine by me. In any case, this ends up looking like 2x minus 7 plus 4 over x squared. So So we put them together, now we've taken them apart. That kind of covers everything I wanted to talk about as far as rational expressions were concerned. I've got a couple more things I want to talk about. The next one kind of ups the degree of difficulty just a smidge, because what I'm going to be dealing with next is no longer really a polynomial. So, cliffhanger.